Before I jump in, I wanted to kind of give just a brief overview of Halliburton. I take it for granted coming from Texas that people understand what oilfield services companies are, but Halliburton is an oilfield service company, so we provide services and technology for oil and gas operators to drill and complete their wells. So that includes things like drilling, cementing the well, producing the well, other services like that. And also just want to say congratulations, you guys have made it to the end of the conference. I know it's no small feat, and so you can take good feelings about that. So it wouldn't be a data science conference without a Venn diagram. And so I wanted to start off with kind of a traditional look at the data that we have. So Halliburton is a 100-year-old company. In the oilfield services industry, we collect lots and lots of data. And we've been doing it for a very long period of time. But unfortunately, we also have a lot of different experts who have unique performance expectations when they go to start a job. So when they're brought on site to do their part of the well construction process, they may be bringing in a new type of technology or trying a different process. And they do that with the expectation that it's going to improve the performance that they're being rated on, right? But of course, that leads to the traditional confirmation bias problem that all of us are subject to. And because there's so much data that we collect, it's easy to fall into that trap just because it's hard to analyze that data, bring into context the historical nature of previous jobs or previous work. And so that really is kind of the heart of the problem that we're trying to solve with this particular use case. So oftentimes we have a lot of historic data from nearby projects. And in the oil and gas industry, we really contextualize things with what we call offset data or nearby wells or other projects that did similar work that we want to compare and kind of learn from. And so just to kind of give you guys an example of the kinds of data that we try to learn from in the data that we collect, over here you see what is kind of a typical, it's kind of a simplified version of a drilling log. So you'll notice in the middle there is kind of, as the numbers go down, as you go down the log, the numbers increase. And this is kind of analogous to the actual wellbore itself. So we measure the data or index it by depth when we view it like this. However, we collect the data as time series. And so that's a nuanced problem that we continually run into. But you can see from the data, those curves on the far left are kind of the inputs. So what kind of commands are we giving to, in this case, to drill a well? And then on the right, you see that very squiggly red line. That's a measurement of ROP, or rate of penetration, which is basically our measurement of how fast we can drill the well. And you'll see that data is extremely varied. It's highly variable data. And again, it's typically recorded in time series, but we typically view it and plot it and compare it via depth series. And so that creates a challenge that we'll go into. And then on a typical project, especially in terms of like drilling, we will collect millions of event-stamped rows of data. And it's spread across hundreds, if not thousands, of tables, combining to maybe thousands of different variables that record. And so sensors that are recording everything from that happens on surface, things that happen downhole, inputs that the users are putting into the system. So we have a large data set with, again, time series data that doesn't match up. So one table might have measurements every 1 second, another table might have measurements every 5 seconds, another set of data may be taking measurements as needed. So a very challenging data set to manage. To make matters worse, when we start to think about combining and comparing data sets, there's some serious challenges in terms of normalizing the data. So when you think about the Earth and the surface of the Earth or the subsurface, you basically have what's a layer cake of different rock types. And so when we drill through these rock types, they change the dynamics and how, in this case, the ROP might be impacted. So think of rate of penetration as your dependent variable here. But that's going to change depending on the type of geological formation you're drilling through. And so from one well to the next, you're going to encounter those formations at different depths. So even though you've indexed by depth, you can't necessarily compare them by what happened at 10,000 feet in one well is relevant to what happened at 10,000 feet in a nearby well. We also have a lot of factors in terms of equipment. So you could be drilling different hole sizes. You could be using different types of equipment down hole in terms of like the bit at the end of the drill string, or other tools that might impact how the drill string performs. And then, of course, there's operational factors like the user inputs, like how much weight do we put onto the bit, or how fast is it rotating. So all of these factors help create an already varied data set, add a lot more variability. And some of these things are even open for interpretation in terms of geological factors and things like that. But for the purpose of this use case, we wanted to optimize the rate of penetration, or ROP. And so the first challenge we would encounter is, or what we wanted to say was, how does the historic ROP indexed by depth compare to a current operation collecting ROP data as you're drilling through the operation? And like you can see, you can collect the data and plot them both against the depth and the y-axis of the ROP there. And then the question is the current well, the one that you're performing in real time, is it doing better or worse, or is the same as your historical offset wells or your historical offset data set? So the first challenge for us is creating that historical operational data. And so we do this with our data lake funnel. So we kind of look at it as a 3-tiered flow of information. I mentioned that we have a very mature industry. We've collected data in a huge number of different formatting types. The first one listed there is a proprietary format called .ADI, which is kind of unique to not even our industry, but also just our company. And then we collect data in terms of Parquet files. LAS file is another industry standard for us. Daily drilling reports, so PDF or Word documents with a variety of different kinds of formats and layouts. But all of this unstructured or semi-structured data, we land through a kind of an automated upload API into our data lake. And we organize that information in kind of a logical framework for our industry. But within that data lake is where we'll store 100% of the data that we collect. It's tagged with the appropriate metadata as it's ingested, but we have extremely limited access to that data in terms of who can access it. It's also very important that we maintain and respect the confidentiality of the data that we collect. So we collect data from a lot of different customers, and it's very important to them that we don't cross-pollinate information from one customer's data to another customer's data, because we have strict confidentiality agreements that we have to adhere to. Then we get into the area where, for like this use case, we say, hey, we want to compare and aggregate all the ROP data, or the drilling performance data. So that's where Spark, and for us, Databricks, has been an extremely powerful tool. We've been able to query the data lake and bring together thousands or tens of thousands of files into one query, do the data engineering necessary. So we could have say in the ADI data is where we have our time series data. And then we have some contextual data, maybe in the Excel files or in the other structured data sets that we collect. So we merge those into kind of a subset of predefined data frames and start to persist kind of an intermediate store. We also use that intermediate layer as a place where we add the context, like some of those geological or operational factors get added into that time series data. And then finally, we convert it into depth-based data. That way, when we go to look at a group of wells as a whole, they're all the data fits into specific depth buckets or depth windows, you could say. And typically for us, that's by the foot, but sometimes it can be more or less granular. And again, in that intermediate layer is probably where most of the data science work is coming from. Users are consuming a lot of these pre-prepared data sets, and we've automated the ingestion based on some prescribed views or interpretations that are typical for us, and so we maintain those data sets in kind of this intermediate layer. And then finally, we get to the traditional BI data sets where we have extremely structured relational data sets maintained in operational data stores. We use things like SQL and Power BI to query and consume that data. And those have kind of a higher operational uptime and availability. And again, it's a very small subset of the data, but it's also very consumable and user-friendly for our analysts and our technologists. So once we've pushed the historic data for a given use case into this operational data store, we then need to combine that with what's going on in real time. So from a real-time standpoint, we have our own legacy architecture and infrastructure for collecting and transmitting data in real time. And again, like I said, as an industry that's very mature, we've developed a lot of our own technologies and standards for this and kind of embedded a lot of infrastructure, physical infrastructure that has to kind of be maintained and will continue to be utilized for quite some time. So when we talk about the streaming aspect of the data, it's coming across in kind of not the kinds of formats that you guys would expect streaming data to come across. So we still have to do kind of a manual export of this information. We have some straightforward ways to do that, but usually when we start to export the real-time data, you're going to get, it's still going to be highly varied. So in this case, if you look at the ROP distribution, it's at least bimodal, if not just kind of very, very varied, and this is pretty typical for us. And so this doesn't lend itself for comparison to offset historical data sets. And so what the data scientists decided to do was try to normalize that data in the most straightforward way possible that they made sense for us. So they started, they worked through a couple different iterations, but finally came up with a bootstrap methodology that would allow them to normalize the sample of the real-time data that we were exporting to create your basic distribution curves. When we moved to doing that from just on their workstation with Python scripts to doing it in Databricks with having Spark-enabled scripts, we saw that it reduced the time to process those kind of sample data sets for comparison by at least 10 times. So that gave us the confidence to say we can start to push this real-time script or push the script through the real-time environment where users could run it and quickly get back sample data sets that they could use for comparison to their real-time data sets. So from there, we just went into basic hypothesis testing, which is coded in a notebook, that while the person in the center who's collecting the data and comparing it to the historical data may not understand what he's looking at, he can, with a few clicks, run the script and get a response back that says whether or not, is this faster drilling or slower drilling, or is it within this, the expected confidence interval that what is occurring actually is an improvement or not. And that's really where we're trying to overcome that confirmation bias that I was talking about before. So a lot of times users will make a recommendation or make a change to the drilling program from one well to the next and say, oh, look, the ROP average is faster than the previous ROP average. Well, that's a very narrow focus of the data, and they really haven't had the ability to, within a timely manner, pull this data out, combine it into a consumable format for this kind of testing, and then feed back to the people who are making decisions whether or not it's actually an improvement or not. So when we deploy the workflow, what we end up having is the real-time data feed is coming in as it normally does. And so, again, we're collecting, sub-second data and then feeding that into what we call our ROCs, our real-time operational centers. And so in these centers, we have a group of experts who are kind of SMEs in terms of the different aspects of well construction. And they're monitoring the well to ensure that it's being delivered safely, that they're creating reports and summary analysis that they feed back to our customers, and also making sure that the equipment is running safely and that we're not going to have a failure. And then we're also giving them access now through the notebooks, a prepared historical subset of data that they can then reference to. So they, with their existing applications, then export their subset data and then have the scripts running in terms of looking at the visualization and the modeling as kind of an iterative process where they're comparing the real-time data that they've collected or a sample of it with this historical model and determining whether or not they're actually making a meaningful difference, or maybe we're going faster, or maybe we're actually going slower, right? As opposed to just relying on anecdotal ideas. So at the goal for us is always minimize the time of operation, especially when it comes to drilling. So in the oil and gas industry, typically the most expensive part of the operation is the rig itself. And so we like to measure performance from one well to the next in what we call a days versus depth curve, which is what's at the top left there. And so basically the idea is you're trying to drill to a specific target depth. And the rate at which you get there as you go from 0 feet down to however many feet it is to the target depth, say 20 or 30,000 feet, you want to see kind of a rate. And the faster you're drilling as an aggregate, you're going to see a steeper curve. And so our goal is always to say, while you can go back at the end of the job and say, was your overall days versus depth better? it may or may not have been, but now that we've brought in the hypothesis testing as well, we can quickly just say, is it statistically significant that we've made a meaningful difference in terms of the changes, and if maybe it's actually been worse. So our goal is always to drill underneath the curve and be as steep as possible that we can do safely. So this process kind of fits into our overall strategy in terms of analytic use case development. So this is a very kind of basic paradigm that I think we all think about. But from an ingestion side, the first thing is we want to automate the file transfer into the data lake. So all of those different file types, we've built some APIs around our data lake that allows any person within the company or any application within the company to transmit files to our data lake, and then it tags it with the appropriate oil and gas industry metadata. And so we standard on what the metadata should be, but we really don't care what the file type is. So those files are stored are pushed into the data lake kind of in an automated fashion, and that's the only way people are really able to access it in terms of upload. And then we obviously track the data with a data catalog. So we run certain scripts upon arrival in the landing zone, read that metadata information, and then take the appropriate action with the file. So some of that data may need to be just moved to its persistence location, or maybe some subset of that data may need to be processed and added to one of those intermediate data sets, and then made available for consumption that way. And then where the notebooks come into play, and where, in this case, the real-time operations centers would come involved, is they would have access to a specific notebook that was made for them that they could then run the scripts as needed. If the customer had an ad hoc query about the performance or whatnot, they could reference that. And then again, we develop new models and data science applications within these notebooks, and just take advantage of the Spark clusters that we have behind them in order to make sure that we have the compute resources necessary to do the work. And then finally, we really want and envision a kind of a self-service, crowdsourced BI environment for our industry. We have a lot of very technical people who understand the technology that they're using and what they're trying to achieve, but they've never really had access to large, kind of ready-to-consume data sets. So we want to push that data out to the users, and they consume it primarily for us right now through BI tools like Power BI. And then we can kind of control access to that through things like the data flows in Power BI, or access to specific data sets based on regional controls or row-level access controls that we push out at that level. So and then underlying all of that, we have our Azure Active Directory as kind of our role-based access controls. So that follows the data from ingestion and persistence all the way through the system. And then each of those notebooks follows a development process that we have in what we call our playbook. So before you initiate a new data science project, you kind of go through a system, a kind of a gated system and a workflow process that maps out what needs to be done, what kind of data you have to collect, who is the owner of that data, and we push that data science workflow through our playbook, and we document that. So if we do one conditional-based maintenance project on one side of the company, and somebody else wants to do a CBM project, they instead of starting from scratch, they'll go back and reference these playbooks, kind of learn what kind of data types they had, what kind of lessons learned they got from that project, and then hopefully iterate more quickly on the next project. And then of course with the notebooks, the scripts are available for consumption, right? So we can quickly share the code that was utilized and allow continued iteration. So for us, because we could reduce the time for bootstrapping and simplify the access to that workflow, it really validated to us that we could bring in large-scale, powerful computing resources into our existing real-time environments, via the web and cloud computing, rather than having to build new infrastructure and make it easy for those existing kind of very experienced people in that environment to consume and add a new piece of functionality for them. And then we could even push this model all the way to the edge where the work is being done. If they have connectivity to transmit the data to our real-time operations center, they probably have connectivity to the internet to run the notebooks from there. So the people who are actually deciding what those input parameters should be on a minute-by-minute basis could have these questions validated as they needed them. And then it finally gives us the unbiased view of the data. So we have, like I said, a very mature industry. A lot of times the person who has the most votes is the person with the most gray hair. And so if they have a biased or anecdotal view of what's going on, we fall subject to their confirmation bias a lot of times. So now we can actually look at the full amount of the data and try to make a meaningful recommendation. And so the actual work in terms of the statistical side was part of an industry paper that a colleague of mine, Peter Kowalczyk, submitted to the industry and presented, I guess, about a month ago. And that kind of goes into the details of what they did from an analytical use case and how the statistics worked out and how they came to the conclusion that they did. Thank you.
If anybody has any questions, we have a mic on the left and the right-hand side.
Hi, thanks for a nice talk. I have a question about the storage in cloud. Since you have a lot of data sources, a lot of data, do you store those data in SQL format, like database, or it's just a raw files based on use case?
Yeah, so for right now, we are using just the raw file store, and we're mounting to the containers directly with Databricks and then ingesting the data into the data frames that way. I think we're still evaluating what might be that intermediate layer in terms of kind of the database for querying against. But right now, we're just, for this sake, we can query the raw files quickly enough. And there's a naming convention behind some of the files and the hierarchy of how they're stored so that we can logically get to the files that we need to with a given script.
All right, thank you.